The most important law of nature is the second law of thermodynamics, much discussed and debated by not only the scientists, but historians, by the economists, and by theologians. It basically says events happen in certain direction. They go from order to disorder, from concentrated to diffuse, from useful to useless, from available to unavailable. It basically defines the arrow of time. We go from the past to the present to the future. The second law of thermodynamics gives us guidance for what we can and cannot do. It tells us how to design better machines, provides us with blueprint for using our resources more effectively. In short, it gives us a sense of direction. As an example, it tells us the heat flows spontaneously from hot object to cold object. Water will flow from high mountains toward the rivers, and if you puncture a balloon, the air would rush it out from inside to outside the balloon. According to the second law of thermodynamics, the universe is continuously slipping into chaos, which we call it thermodynamic equilibrium, where all non-uniformities in temperature, electric potential, pressure, etc. vanish and eventually reach a heat death. Accordingly, it predicts that earthquake flattens buildings, decreasing order. Similarly, air, as it gets warmer, the snow is expected to melt, going from a state of high order, which is ice's lattice structure, into disorder, which is unstructured liquid. The best measure of disorder is entropy. Entropy is from the Greek word meaning transformation. It is a way that shows how different configurations can be made. For example, a deck of cards, which is ordered in a certain way, is it perfectly ordered. As you reshuffle the cards will be totally disordered. The number of ways that this configuration can be arranged is a measure of the entropy of the system. Entropy was defined by Ludwig Boltzmann, and basically it shows that as we go from the passing to in the time, the total disorder in the universe or the entropy of the universe is constantly increasing. Well, if you take 2 teaspoons of salt and pepper, these are in highly ordered form. However, if you mix them, then it will be very, very disorderly. You cannot distinguish the salt from the pepper. In a way, the whole action of mixing has increased the entropy. As you probably guessed, right? It takes a lot of effort to separate the salt from the pepper, but it takes relatively little effort to mix them up. That means going from order to disorder is very, very simple. However, getting order back is very difficult. These are some other examples of what the implication of the second law of thermodynamics is. It says that the electricity will turn into heat, but it's difficult to turn back to electricity. So these are some of the consequences of the second law of thermodynamics. It says the heat, which cannot by itself from a low temperature to a higher temperature, because lower temperature is a state of lower entropy, and the higher temperature is a state of the higher entropy. The lower temperature is a state of lower entropy, higher temperature is a state of higher temperature entropy, and that cannot be done. Or in a way, work which is a very low entropy cannot be converted to the high entropy, which is heat. In other words, heat cannot be converted to work, but the work can be easily converted to heat. We know that from our experience that we push, a cart, eventually all the work, the muscle work in our hands, will be transferred into heating, the floor and the wheels of the cart. However, I cannot cool the cart and let the cart to move back and produce work. It is important to realize the distinction between the second law and the first law of thermodynamics. Basically, first law of thermodynamics is a quantitative law. It does not make any distinction between different form of energy. Energy is energy. If I have 100 BTUs in the form of the work or mechanical work, it's exactly the same thing as 100 BTU of the heat. However, the second law of thermodynamics puts a limit on how this energy can be manifested. In a way, it tells different forms of energy, they have different quality. So second law of thermodynamics is a qualitative law. In a way, it tells you that if I have 100 BTU of the work, we can do more with it than if I have 100 BTU of the heat. Third law of thermodynamics is talking about absolute temperature. It says you can cool down something, but you cannot cool it infinitely. You can cool it down, the temperature will be lower and lower, but as it approaches the temperature of minus 273, then you cannot be cooled any further, and that will be absolute zero temperature. Basically, at that temperature, all the molecular motion stops. So after that, any kind of removal of the heat is impossible. That is considered to be third law of thermodynamics. So these are a number of questions which gives you an impression how much you know prior to taking this unit. For example, and these are usually misconceptions among people. The first question is it true or false? Energy is conserved only if no friction is present. Well, many people think, that the friction is the reason that the energy is not conserved. Well, actually, energy is conserved whether there is a friction or not friction. It's a matter of taking into account the frictional losses, and then energy becomes conserved. The second question is energy can be converted from one form to another. That is true, and that is the basis of the first law of thermodynamics. Work can be entirely converted to heat and vice versa. In the following slides, I will show you that work cannot be converted to heat, work can be completely converted to heat, but heat cannot be converted to work. So from work to heat is possible, from heat to work is only partially possible. And finally, an ideal heat engine that works with no friction is 100% efficient. I will show in the following slide that this is not correct, and the construction of a time machine, also possible, must wait for a very long time, and that is also in violation of the laws of thermodynamics. This is the answer to the question of the 100% efficiency. This is a heat engine removing some heat from high temperature 2000 degrees Celsius and dumping some of the heat at the temperature of the exhaust at 100 degrees Celsius and taking the rest of it and converting it into the useful work. Well, if it was 100% efficient, that means we did not have to dump any of this heat to the exhaust. In this case, all of the Q in would get into the W out. That means that we are converting from disorder to order, and that is in violation of the second law of thermodynamics. And the same thing is true for the refrigerators. Refrigerators require some kind of energy input. That's in the form of electricity. So we cannot remove heat from a low temperature and dump it at a higher temperature without expenditure of the energy. If we could, then we had moved the created order without using any work, and that is not possible.